Question 7 says, prove or disprove if a is any odd integer, then a squared plus a is even. So I like to do a couple tests first when it says prove or disprove, because I need to decide, am I going to try to prove it? That's pretty hard. Maybe disproving, if it's not true, disproving is easier. So a is any odd integer, so let's do a equals 5, right? Then a squared plus a is 25 plus 5, which is 30. That is even, so that works. Maybe one more. Let's do a is 11. So 11 squared plus 11, that's 121 plus 11 is 132, which is even. Okay, I think this is true. So I'm going to try to prove it. All right, so what I say is you suppose the if part is true. So suppose a is an odd integer. And I need to show that a squared plus a is even. Okay, so since a is odd, a can be written as 2 times an integer plus 1. So a equals 2k plus 1 for some k in z. Thus, a squared plus a would be 2k plus 1 squared plus 2k plus 1, which is 4k squared plus 4k plus 1 plus 2k plus 1, which is 4k squared plus 6k plus 2. And I can factor 2 out of every one of those terms. So I have 2 times 2k squared plus 3k plus 1. Now, 2k squared plus 3k plus 1 is an integer because multiplying two integers gives an integer and adding two integers gives an integer. So this whole thing is made up of multiplying and adding integers, so it's an integer. So I just need one last sentence that says, since 2k squared plus 3k plus 1 is an integer, a squared plus a equals 2 times an integer, and so is even. Number 8, prove or disprove. If r and s are any two rational numbers, then r plus s over 2 is rational. So it's just saying that the average of any two rational numbers is rational. So we have proven that the sum of two rational numbers is rational. So I'm thinking that a rational over a rational will be rational, and I'm not going to do any testing. I think that I can go ahead and just start to try to prove this. So we're going to suppose the if part of the statement, that r and s are two rational numbers. Suppose r and s are elements of the rationals, which we denote with a q. Then r can be written as a over b, and s can be written as c over d, with a, b, c, and d all being integers, and importantly, b and d not being 0 because they're denominators of the fraction. Thus, let's see what we get when we calculate r plus s over 2. So I would have a over b plus c over d all over 2. And then simplifying just the numerator, just get a common denominator. So I would multiply a over b by d over d, and c over d by b over b. And I have AD over BD plus BC over BD. And then instead of dividing by 2, I think I will, actually, I'll just divide by 2 for now. Okay. All right, now when you add two fractions that have the same denominator, you just add the numerators. Keep the denominator the same. And now, instead of dividing by 2, I can multiply by a half, just multiply by the reciprocal. So this ends up AD plus BC over 2BD. So I have now written this as an integer over an integer, right? Because A, B, C, and D are all integers, and sums and products of integers are integers. So 2BD is an integer, and I have to make sure that 2BD is not 0, which, because neither B or D can be 0, it should not be 0. So I just need to write that all out explicitly. So I can say since AD plus BC is an integer and 2BD is an integer and 2BD is not 0 by the zero product property, right? Saying that the only way you can get a product to be 0 is if one or both of the factors is 0, and we know that neither of them is 0. That tells me that 2BD is not 0. Then R plus S over 2 is rational.